Thank you very much. It is a pleasure to me to introduce our first virtual speaker. It is Dr. Vittoria Sposini from Universität Wien, and the topic of her speech, non-Gaussianity and random diffusivity models. Okay, please.
Hello, can you hear me? Hopefully, yes. Okay, perfect. Thank you. Okay, good morning, everyone from Vienna. Thanks to the organizers for having me here, even if online. And today I will talk a bit about my my work on non-Gaussianity and random diffusivity models. And before starting, I'd like to acknowledge my co-authors. All the results that I'm going to present today are basically from two papers, which are joint works with my co-authors here. So Ralph Metzler, Danny Pagnini, Alexei Chechkin, Gleb Oshanin, Denis Grebenkov, and Flavio Seno. So I'd like to acknowledge them all. And let me start with a brief outline of my talk. So I will first provide a general overview of what I mean by random diffusivity models, and then I will mainly discuss two examples, two cases, the cases in which the diffusivity is modeled as a jump process, and then the case in which diffusivity is modeled as a continuous process. And finally, I'd like to just give you a quick overview of why these models are relevant, in particular connecting them to the concept of Brownian non-Gaussian diffusion, which has been observed in experiments more and more often. So starting from the concept of random diffusivity model, I hope that you can see my pointer as well. The general framework that you can see over here of these random diffusivity models is basically that if we define with x the position of the particle that we are describing, basically you can see that the increments of these particle positions are given by the increments of the Wiener process times some time dependent amplitude. So in particular, this d0 that you see over here is a positive dimensional coefficient that is constant and of course includes all the dimensions of a diffusion coefficient, as you can see over here. W, of course, Wt denotes the Wiener process, and this psi of t is a positive definite time-dependent random function that defines our time-dependent amplitude in a way. And of course, this framework is not new, was borrowed by somehow very well-known work. And in a way, you can immediately recognize that clearly if psi of t is 1, we have standard Brownian motion, while if psi of t is a deterministic function, and in particular is a power law, what we obtain is a scale Brownian motion, which is a well-known model for anomalous diffusion, which is able to reproduce both super diffusive regime and subdiffusion. On the other hand, you can also think of this psi of t actually to be just a random variable if you forget the time dependence. And in particular, if this random variable is distributed according to an M-right-Mainardi function, then somehow you will see that this framework will resemble in a way the generalized gray Brownian motion. So somehow this just to give you an idea that the framework is quite standard. It has been used already before. Just here we are introducing clearly kind of a random amplitude, which is also time dependent. And just a note to make my talk as clear as possible, psi of t is a dimensionless variable because as you saw, all the dimensions are included in the coefficient d0. However, I'll still refer to it as a random diffusivity. So whenever I talk about random diffusivity, I always mention this psi of t, and this is also why we define them random diffusivity models. So in order to have a very general solution of random diffusivity models, of course, regardless of the choice of your random diffusivity, you can rewrite your x of t in this way. I remind you that our random diffusivity and the Wiener process are totally independent. And then we can calculate the characteristic function of our x of t, which is written in this way. So let me point the attention to the fact that we have two averages here. So basically you have the line, the bar on top, which denotes the average over the Wiener process So what we call kind of the thermal history, while the angular brackets, they denote the average over psi, our random diffusivity. So if we perform the first average, which is over the Wiener process, then we obtain this result over here, and you immediately observe that actually the characteristic function of our process depends mainly on this quantity, which is the integrated random diffusivity. So if we rewrite this integrated random diffusivity as a tau of t, then you can immediately recognize this formula here as actually to the moment generating function of this integrated diffusivity. So with this result, you see immediately that basically the characteristic function of any random diffusivity model can be directly linked to the moment generating function of the integrated random diffusivity that we call tau. And its moment generating function is calligraphic capital T over here. Of course, here you can immediately see that in a way you could solve these models also with a subordination approach, which we've heard a lot during the workshop. And indeed, you could use a subordination approach, and this tau, so the integrated random diffusivity, would kind of be your subordinator in here. The main result is that, okay, since we link the characteristic function to the moment generating of the model to the moment generating function of the integrated diffusivity, you see immediately that the probability density function of a random diffusivity model can then be obtained by inverse Fourier transform of its characteristic function, which is then exclusively defined by this moment generating function of the integrated diffusivity. And very interestingly, we can also connect the variance of our model to the first moment of the integrated diffusivity when it exists, of course. So in a way, this is just a very general way to treat this kind of random diffusivity model, regardless of the choice you have for your random diffusivity time. So we will keep in mind these results for the whole talk. Let's now consider some examples. Let's define our diffusivity model as a jump process. So very intuitively, what we do is that we imagine that we have an observation time, capital T, and we have this time interval between 0 and capital T, and then we divide this observation time in capital N sub-intervals. Each interval will have sub-interval. We have a duration of delta, which is of course capital T over capital N. And then we suppose that our random diffusivity is a jump process on these intervals, meaning that it obtains a new value psi of k on each sub-interval. And these values psi of k are just positive definitive IID random variables which are distributed according to a certain distribution that we call rho of psi. Now, for a given realization of the process, we know that what we have to look into is actually the integrated random diffusivity, which is what we have capital, which is this tau. And then you can see that actually this integral in this case of jump process will become a sum, and the integrated random diffusivity is given in this way, such that the moment generating function of the integrated random diffusivity can be written in this way. And from that, we can also calculate the first moment of the integrated random diffusivity that we know is very important because it relates to the variance of the particle position. And this is given by our observation time, capital T, times the average of our psi, of course, when this average exists. These are basically the main results for the case of diffusivity model as a jump process. Let's consider two examples. So in the first case, if we consider, for instance, the case of a Lewis-Smirnov distribution for the jump process, so we imagine that the value of our jump process are taken from this Lewis-Smirnov distribution, then we can, from this formula, sorry, I go back, that I explained you here before, you can see that actually the moment generating function in this case becomes this exponential, such that the probability density function of the particle position is given by a Cauchy distribution. And this somehow makes sense because here we introduce for the jump process a Lewis-Smirnov distribution that doesn't have a finite value, and we obtain indeed for the particle a finite average for the first moment doesn't exist. So basically what we have for the particle PDF is that we have a Cauchy distribution with a variance that is not admitted. So indeed this makes sense with our result over here, where we said that the first moment is really related to the moment of our psi. So this was just to give you a general, an example to give you an idea of what happens if we select such distribution for psi. But what is of more interest to me, and let's say for my work, is in the case in which you actually assume that our jump process is distributed according to a gamma distribution. So let's say that we have a gamma distribution which is defined in this way with a parameter mu which is greater than zero, and I recall that this the average value of psi in this case is just mu. And we can again calculate the moment generating function of the integrated random diffusivity, and we obtain this result that is shown over here. And as a consequence, basically the probability density function for our random diffusivity model is given by this formula over here. So capital N is just a normalization factor, and K is a modified Bessel function of the second kind, which we know it's basically an exponential decaying function. So this is the main result for the case in which you have a gamma distributed jump process. I would say that very interesting to see that basically in this case, we have a functional behavior for the probability density function that strongly depends on the ratio between your observation time and the delta. I remind you that delta is the length of each interval, of each sub-interval. So basically, you see that depending on this duration, we can observe this different functional behavior of the probability density function. All of these, when actually we have that since the average value of our gamma distribution is just mu, the variance of the random diffusivity model will be just linear. So basically, all of this happens while the variance of the random diffusivity model is linear in time, so almost like as it is for Brownian motion. But here we obtain a probability density function which has a very interesting shape, and it can actually change depending on this ratio between t and delta. And just to kind of give you an understanding of what happens, let's consider two limits of this ratio. So for instance, if we take the limit of delta that goes to t, to capital T, this means that actually we are selecting just one big interval, and we are taking basically a jump process. I mean, our random diffusivity is no more a jump process, but it's just a random variable, which has a fixed value for the whole duration time of the process. Then what you observe is that actually our probability density function becomes this formula here, which is again, of course, Bessel function of modified Bessel function of the second kind, defined this way. And this result makes sense because we can also actually obtain it in a different way. As I told you before, since we are taking the value of delta that goes to t, basically we are assuming that our random diffusivity doesn't have a dependence on time anymore within the observation time. And this means that actually going back to our general framework, we can just take it out basically from the time dependence, and we can just rewrite our process as a Gaussian process times a random amplitude. And in this of course, the probability density function then can easily be obtained by means of this integral over here. And this is what you would obtain if you, for instance, check the results on the superstatistical Brownian motion, which was introduced by Beck in early 2000. So somehow the results obtained from these random diffusivity models in this limit of delta that goes to t go back to what is commonly known as superstatistical Brownian motion. So I think it's very interesting and it makes sense. And indeed, if you solve this integral, what you obtain is indeed this formula over here. Now, if we instead consider another limit, the limit in which delta goes to zero, of course, in this case, we have to be careful. We consider delta that goes to zero together with the capital N, so the number of intervals that goes to infinity, such that their product is constant and is equal to our observation time, capital T. And what is interesting is that in this case, actually, we go back to our like framework to solve the random diffusivity models, and what we obtain is actually approximately a Gaussian distribution for the particle displacement with a diffusion coefficient that you can see can be defined as actually the average value of psi times d naught. In this case, or in the case in which actually delta is very small, let's say, so we have a lot of jumps within the observation time, our probability tends to be a Gaussian again. And I also performed some Langevin, like Monte Carlo simulations, and indeed you can see that depending on the value of delta, you obtain very different functional behavior of the probability density function. Here, our observation time is 100, so you see that basically here delta and observation time are the same, and we are in this strongly non-Gaussian regime. While if we take delta, which is equal 1, we can already see that our PDF is well described by a Gaussian distribution. This is somehow very interesting because we have a framework in which we are describing somehow a transition in a way between a non-Gaussian and a Gaussian distribution, because indeed you could think of what matters is the ratio between delta and capital T. So you could imagine of keeping fixed delta and changing your observation time, and depending on when you're where the observation time is in respect to delta, you will observe different functional behavior of the probability density function for your particle position. And similar results can actually be obtained in the case in which you model your diffusivity as a continuous process. So instead of having a jump process, you can imagine that your random diffusivity is a continuous process, so just a random a stochastic process. In order to ensure that it's positive, because we want it to be like a kind of a diffusivity, we want it to be positive, we define it as the square of some auxiliary variable y, and then we define the stochastic equation for y. Again, here is a Wiener process which is independent from the one we defined for the particle position. And then it's kind of interesting to see that we can, in a way, start from a certain distribution that we want for the random diffusivity and define the parameters for our stochastic equation for y. So indeed, if you set the distribution for your random diffusivity to be rho of y, you can then, of course, calculate the distribution for y since they are related in this way. And then assuming that you want a stationary distribution, it's possible basically to see that to check that, to impose that the drift term in this equation is given by this equation this formula over here. So in a way, you can adjust this framework to your to the distribution of this random diffusivity that you want to have. And this is something interesting because in a way, the distribution of the diffusivity could be something that you can extract from, or you can in a way observe from experiments. And in this, so if we model the diffusivity in this way, basically in particular, we could again select a distribution which is, let's take instead of a simple gamma distribution, let's take a generalized gamma distribution, which we include also a stretching exponent here or compressed exponent here, compressing exponent here. So it is eta. And in this case, also the first moment, of course, is given according to this formula over here. And following the scheme that I told to you about in the previous slide, basically you can define what is the stochastic equation that you need for y in order to obtain this distribution for your random diffusivity. And it is very interesting to see that in the case in which you select eta equal 1, so basically we just go back to a standard gamma distribution. And in particular, if you have u, which is 1/2, this equation for y becomes a non-Uhlenbeck process. So you can really see that basically you have somehow a value a value of your random diffusivity, which is oscillating around an average value. So this is basically just a very general framework, and you can solve it similarly to what I discussed to you before for random diffusivity model. And it's very interesting. I think it's very interesting that you can perform a similar analysis to the one described for the jump random diffusivity case. And basically, even in this case, the PDF shows two limiting behaviors. So in this case, before we had the parameter delta that somehow played the main role, while here the main role for the two limiting behavior is played by this, what I call tau star, which is basically the relaxation time for the diffusivity dynamics. So if you go back to your equation for the diffusivity, from here you can basically derive what's the relaxation time for this diffusivity of the autocorrelation function, and you can define the time scale for this model, and you can see that at short times with respect to this time scale, actually the PDF of the particle can be well described by our super statistical Brownian motion, as I showed before also for the jump process. So we obtain some non-Gaussianity in here, while if you go to very long times, so times which are longer than our tau star, you can see that the probability density function turns into a Gaussian. And again, here I'm showing you some plots from simulations of the Langevin set of Langevin equations, and you see that indeed here we have that our tau star, so the time scale is around 1, and for times which are shorter than tau star, you see that you really observe like non-Gaussian distribution according to results that come from this integral over here. While if you go to times which are longer than this tau star, you really recover a Gaussian distribution, and all of these while the mean square displacement is linear in time. So basically, we have an interesting result, basically, that we are able to show that we kind of reproduce this transition of the probability density function without actually changing the trend of the mean square displacement. And in a way, I just wanted to dedicate the last 3 minutes to kind of tell why are these models relevant and why we are interested in studying this model is, okay, in general, we thought that they represent kind of a nice mathematical framework for studying different kind of diffusion processes within a unified approach, which is, okay, nice. But in particular, actually, the case that I showed you with the gamma distributed or generalized gamma distributed random diffusivity, we saw that they provide a good mathematical description for what is defined as Brownian non-Gaussian diffusion. And this is a kind of diffusion that I showed you already is kind of characterized by non-Gaussian distribution with exponential tails, possibly a transition from this non-Gaussian to a Gaussian at long times, and all of these combined with a linear trend of the mean square displacement. And this is very relevant because actually this Brownian non-Gaussian diffusion was observed in many different physical systems. Here I'm just reporting 2 or 3 to give you an idea of how this is really like kind of a universal behavior, it seems. So for instance, you can see this was in 2009 from Granick group. This is probably the first paper that brought attention to this kind of behavior, even though then we saw that there were many more which were already even earlier in time. And you can see, for instance, here on the left, you have these green particles which are diffusing along these nanotubes. And if you look at the mean square displacement, you see that this is very well described by a linear trend, so it's linear. But then if you look at the displacement distribution, you see that this is a semi-log scale, and different colors correspond to different times. So at short times, for instance, the blue and the green, this is clearly exponential, while at long times, it tends to a Gaussian distribution, as you can see from the red curve. So indeed, you see this clearly what we mean by this Brownian non-Gaussian diffusion, and this something similar happens also in the case of a 3D system here, where you have a particle diffusing in some entangled network. Or for instance, if you study a totally different system, which is the dispersion of these little worms, which are called nematodes, and you also obtain from this plot over here that basically the distribution is not described by this dashed line, which is a Gaussian, but it's actually described by this linear line, which is in a semi-log and exponential trend. And another case also where there's these very nice experiments when they really try to reproduce the environment, some sort of random environment. And you again see that I'm not going into the details of the experiment. If you want, here is the reference, but looking at the plots, you see that depending on how the environment looks like, basically you can have always a mean square displacement that grows linearly in time, and yet a distribution that starts displacing some non-Gaussianity. So in a way, this Brownian non-Gaussian diffusion seems to be relevant, very relevant for different physical systems. And within this random diffusivity model approach, I think that somehow it's possible to show how these features can come across from a mathematical point of view. And I think my time is basically up. So with this, I think that I would just like to conclude by mentioning that the main results, all these results are discussed in these papers over here. And here you also find some other literature on random diffusivity models, diffusing diffusivity models, because of course many other people work on that. And these are some references. It's not a complete list, but if you're interested, I can provide, of course, even more references. And thank you all for your attention, and I'm happy to answer any questions.
Thank you very much, Dr. Sposini. Do you have any questions or comments? Yes, please.
Thanks for the talk. I was wondering about two things. First, if you have the PDE that is solved by, let's say, the expectation with respect to this random diffusivity process of a certain initial profile. Like, have you studied Feynman-Katz type of solution, representation of the solution of a certain deterministic PDE associated to this random process?
Okay, no, this we didn't do at all. But okay, that's a good suggestion.
Oh, okay, and then maybe if you also started to consider this random diffusivity that depends on the particle itself, or maybe even processes of particles that have this diffusivity that depends on the, for instance, the instance of the particles in the system, or if there are not at all studies regarding these possibilities.
So you mean if the diffusivity depends on the, what do you mean, like depends on the particle?
On the particle itself, is in this case, I think you presented everything where the diffusivity is depends on some other stochastic process that is independent with respect to the location of the particle, right?
Okay.
But you can imagine that in certain materials, like the diffusivity depends also on the amount of particles that are present in a certain region of the material. So I was wondering if there is something like that in the literature, or you maybe even...
Okay. Yeah, so you mean like if it is possible to include some features of the system within this diffusivity. So actually we didn't do it, and we kind of have the idea that this model is a sort of coarse-grained model to describe in a way what you're saying. But of course you could go into some deeper level of descriptions and try to introduce some features of the particles or of the environment. But within this model, we didn't do it because the idea is that we kind of coarse-grain everything that is around. But of course, you can include something like that.
Thank you.
Thank you.
Thank you very much. Let's thank speaker again. Thank you. And